So, define the term pathogen. You said anything that has the potential to cause disease, something that can cause disease. Not all pathogens are always causing disease. Some are opportunistic, but they have the potential to cause disease. What exactly does DNA stand for? That was one of the things I did ask you to know, right? So you wrote deoxyribonucleic acid, and hopefully you spelled that correctly, you wrote it correctly. So explain quorum sensing. I just mostly wanted you to say what is it and what's the significance of understanding it. And you could have been as brief as saying it's how bacteria communicate with each other, between each other. And it's significant because we might be able to use it to fight bacteria, right? So that's all I wanted, right? If you were thinking it was tougher than that, then going forward, you'll know that that's kind of, I want you to getting the gist of things is way more important sometimes than, picky details. So exactly what does MRSA stand for? Again, I think I had asked you all to know, right? So methicillin resistant, and as long as it's phonetically correct. If it's not something I've asked you to know exactly, then please try it. Try it. Try to do it phonetically correct if you can. Methicillin resistant Staphylococcus aureus, you wrote, right? Explain the difference between presumptive and definitive diagnosis. Presumptive means you think you know what it might be. You're assuming, but a definitive means that you have actual data to back it up, the diagnosis, like a culture. In microbiology, we're talking usually about a culture or some sort of immunoassay that would give the result that you know exactly what you're dealing with, right? So again, just a few words would have done that. And this next one, see, my head was either, I don't know whether that was slower, my mind was slower than my fingers typing, or faster, I don't know what. But antibiotics, what I had meant to say were antibiotics may be successful against blank infections, and I've had bacterial infections, but have no effect on blank infections. And so you could have put a lot of things, but most people have usually are viral infections. They're way more common than any other type of infection. And actually that's kind of good news because most viral infections are very self-limiting and the body's immune system is going to be able to take care of it, right? But there are other infections too, like protozoal and fungal and whatnot, helminthic infection. But anyway, those would have worked. What is meant by the mortality rate of the disease? Would you put, Caitlin? Oh, did I pick on you twice? Who wants to say, what's the mortality rate of a disease mean?
It means the number of people that we expect to die.
Yeah, the number. So there's always, for every infectious disease we know, there's always an expected number of cases we're going to have every year or every season. There's always an expected number. And of those that get it, there's an expected percentage that will die. So some diseases are what we call kind of mild diseases because they have a really low mortality rate. But if you're the one that dies, you care, even if it's one with low mortality rate, right? But that is exactly what it means. Define etiology, what was that?
Etiology, what the origin of the disease and what
so
causes it?
Yes, so it's a study of the cause of disease or the origin of the disease. That's exactly right. And then I thought this was fair. What causes strep throat? Because I had given it to you, hadn't I?
Yes.
What causes strep throat?
Streptococcus
Streptococcus pyogenes. Good job. And then what is meant by an opportunistic pathogen? What I kind of wanted you to say was that these are microbes that are always present, even in your microbiome, and they're usually silent and fine because they're in really low numbers. But if given the opportunity, they can cause you to be sick. Right. So what does the term microbiome mean? Who
Make a view that's already in the DNA.
Well, not in your DNA, because you've had DNA, but they have their own DNA, their own little living entities living in and on you. But it's all the microbes that live in and on you. It's your garden. It's your floor. It's your microbial garden, your microbial garden. You know what question I didn't get to ask? Go ahead, y'all laugh at me, make fun of me. That would be mean. But you could do it. I didn't get to ask, what does microbiology mean? I didn't get to ask that. Every anatomy and physiology class, the first quiz is going to have define anatomy, define physiology. I didn't get to ask you all, what does microbiology mean after the first class, because I don't think I told it to you. So I wanted to be fair, but I know that you all could break it down Ology means the study of, micro means small, and bio means what? Life. Bio means life. So the study of microscopic life, really, right? Very small life forms. So make sure we do know that, all right? Great. Now, before we actually get started today, and another day was kind of cool introduction, but before we get started today, I actually do want to tell you what I just handed out to you. You want to keep this, and I don't want you to worry or even think about this now, but in about a month from now, in about 4 or 5 weeks from now, we kind of get going. I'm going, and this is in your syllabus, this thing about this case study presentation. And actually, and always, I have never had it hurt a student. Now, let me take that back. I had one student who hurt because that student didn't do theirs. And so that student had a 0 on, and this is counted as a test grade. But every other student, it really boosted their test grades up. Because this is, listen guys, I don't want anybody to get nervous about this or whatever. How many of you would say that you hate presenting in class? All right, well, okay. I know, and that's why that one student didn't do it. They absolutely were physically ill and couldn't do it. So I ended up doing a little bit something different because they had done the presentation where they had it here but couldn't do it. So they got some points, but they certainly, I couldn't get full points, right? But I do things like by the time we were doing this in that last few weeks of class, y'all, we're gonna all know each other. We just in here. You can sit where you're sitting, You can sit where you're sitting. You can use, I've got a little thing that you can point and progress the slides. I do understand that speaking in public is the #1. Did you know that that's the #1 phobia that people have for speaking in public? So I don't think I don't get that. I cannot speak like on a stage. And people say, well, what do you mean you have that phobia? Because you teach. I said, because when I teach, I'm not feeling like I'm speaking in public. I feel like I'm in here together with people. We're talking, If I felt like y'all felt like that about me, I'd probably be tongue-tied and not be able to speak at all. You're right? Because I do get that. But I don't want you to be nervous about it, and I wanted to help you. Let me just tell you a little bit. You got a rubric that sort of tells you where your points come from. And on the back of it, you'll see from your ebook and digital book, and by the way, the 3rd edition might be slightly different pages, but I'll figure that out. I am actually going to, in about a month or so, by then I'll have a better idea. I might try to assign these microorganisms because like C. diff, already knew a lot about C. diff, obviously, so that's something that you know about. But it might be that, as far as West Nile virus or something about RSV, respiratory syncytial virus, you have a special interest in, and you might come to me and say, look, I think I'd like to do that case study because I have a child who had that, and I'd like to know a little bit more about it. So I'm going to assign these within in another month or so. I'll assign them, and it's not that big of a deal. I don't think it'll take y'all that long to come up with either a few slides on PowerPoint, or if you wanted to, I've had students do a poster. They did a poster where they printed out pictures of patients who had gangrene, let's say, and they did whatever, and they talked a little bit about it, right? And it's only 5-10 minutes, I'm telling you, not too long. It doesn't have to be very long. All right, so we'll talk more about it, but y'all read through this and realize this is a test grade, and this is actually not supposed to hurt you. This is supposed to help you, all right? And the thing about this, I used to do a required research project from you guys. So you have to pick a disease, an infectious disease, do a research project and give it to me. And I was thinking, well, this is so crazy. I mean, it's not like I know every disease, but I know about these diseases. I want you all helping each other. I want you all talking to each other and knowing, hearing a different voice with these diseases, because it will help you to remember when you get on the floor someday or wherever you might be, and you have somebody who has gangrene. How many of you have seen gangrene? If you've ever seen it, you know it, and it's just whatever. But you might be thinking, I do remember something about this, and I remember, because you'll hear each other's voices at the time. Okay, Claire, this is supposed to be relaxed. Are you relaxed? Okay. Sweet. Put them away for now, but this is just what it's meant by that case study presentation counting as a test grade that you see in the syllabus, okay? And this is the rubric. So where your points will come from comes from here. Okay, so I wanted to just give you all that so that you can be thinking about that. Do I have any questions about that?
So you're gonna assign one of these to us?
Yeah, I am. In about a month, when I'm talking, and maybe in a month's time, Haley, something will come out, and I'll know. I know you right now have Brantley, right? And so you might be really interested in RSV because you're hearing that, you know, it's the #1 cause of hospitalizations of infants, right? Or whatever. So I'll find out more about you all, and I might say, would you be interested in doing this, you know, and whatever, or do you have an interest? So I'm gonna try to make it both ways. I'm not just gonna give you something you hate. You know what I mean? A topic that you hate, but I'm trying to figure out more about you and figure out which one might be good for you. If you look at it and you look at the topics on these, because it's in your text, most of what you need is just right from your textbook. So you just go to the ebook, read the section on it, the case study, and there's a follow-up, read that, and try to cover that. So the first little part of your presentation is just sharing that with the rest of the class, because they probably are not going to read your case study, you know, and so they're going to not know who the patient was that was presented and what kind of signs and symptoms they came in with, right? So if y'all look over this, and I know y'all are, so all of y'all are all type A personalities because you're going into medicine. So probably by the next class period, a lot of you are going to be coming to me and saying, can I have that topic? And that's fine. If you see one that you really like, come to me and we'll put you down for it. But I can't have anybody repeating it, right? So look over it. If there is one that you really think you want, then I'll try to give it to you. All right. Good? Are we good? Do I have any questions for me about this? Okay. So okay, let's go ahead and continue on. Did I stop in a place that I told you I would pick up right there? Because sometimes I do that and then I forget to pick up there. But okay, if I didn't stop, we'll go ahead and start right here. We know what the definition for microbiology is, right? And under microbiology, I would like you to also understand that there are sub-disciplines under that umbrella of microbiology. The study of microscopic life. So there are all kinds of subdivisions underneath that. Bacteriology would be what? Yeah, really the study of bacteria. Virology, of viruses, is that right? Viruses. Mycology, M-Y-C-O, mycology is the study of fungi. So see, under microbiology, if you go into pathology, where microbiology is a subdivision of pathology, one of the subdivisions of pathology, in microbiology, you typically can be a generalist where you would work in all of those labs, virology, bacteriology, mycology, or you could specialize, right? So just to give you kind of idea of how this is all organized, right? I just want to have you have that introduction to that. But when we think of microbiology, we are often, unfortunately, giving all of our attention to the bad guys, the pathogens. The pathogens get all, you know, it's just like people in the classroom, you know, the squeaky wheels are the ones that get you all right. But anyway, but I need for you all, even though we're going to always be concentrating on the ones that cause disease, I need for you all to know that we can't live without our friends and the good ones. And the bad ones only number in the very, very few. Most microbes are actually doing really wonderful things for us, like putting oxygen in our atmosphere, recycling nitrogen. But most of them are doing amazing things for us and allowing us to be healthy. So we can never, please never, ever forget that and have that in the back of your head. Let's look at some of the things that they are doing. If there's enough of the good guys around, guess what? The bad guys will never be able to increase in numbers enough that they can turn on those virulence factors. You get what I mean? We have to keep our good ones in good enough numbers. Go play in the creeks. Go play with some dirt, right? Go do some stuff like that. That's okay. That's all good. It keeps our immune system strong, and it's good. Our microbes actually educate our immune cells, our immune system. Let me tell you where that starts. That starts as soon as the amniotic sac breaks. Y'all call that the water breaking, right? When that amniotic sac breaks that the fetus is in and the water breaks, microbes from the mother's vagina are being introduced into the amniotic sac thing. And the fetus is getting introduced to vaginal microbes. Let me tell you about a vaginal microbe and this is just one of many. It's called Lactobacillus. That's the genus. Lactobacillus. One word. Lactobacillus is a genus. Lactobacillus. L. Lactobacillus with a B. B. Bacillus with B. So lactobacillus. That should be, for all of us ladies, that should be one of the predominant microbes in our vaginal area. Is Lactobacillus. The genus is called Acidophilus, but right now just write the genus name, which is Lactobacillus. Guess why that's important for the fetus to be introduced to? Guess when the fetus gets introduced to that, the fetus swallows that, and it ends up colonizing in the fetus's colon. Guess what it helps the fetus to digest? Lactobacillus. What do you get? Milk. 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 It helps. So that's just one example. There's so many microbes in the vaginal secretions that are protective and introduced to the fetus, will help the fetus's immune system start this process of understanding what is friendly and what is foe. We are just beginning to understand how important it is so much that some hospitals, actually many of them now, are doing this. Thank goodness. Mothers that have to have C-sections, they're taking swabs from the mother's vaginal secretions and wiping the C-section babies with it. They're understanding there's certain things that over the decades since we've been doing C-sections, we know that C-section babies are way more at risk for some things, like even obesity later, and opportunistic diseases that we don't see in vaginal. Just the numbers tell us that there's a difference in how a C-section baby might respond to its environment that's different from vaginal delivered babies. So you know what? They're trying that now. They're trying to do that. That's kind of interesting, isn't it? It's kind of cool to think about that. So our normal microbiome, and we start to get introduced to it really essentially as soon as that amniotic sac breaks, is doing these things, protecting from pathogens, educating the immune system. Without the microbes in your colon, your large intestines, you can't finish the digestive process. You cannot. So nutrition would be affected if you didn't have those in your colon. So providing nutrients, vitamins, there's many vitamins like E. coli. Y'all have all heard of E. coli, haven't you? You've heard of E. coli. E is, well, I should probably tell you this now. E, after you say the genus one time, and then the species is coli, after you say the genus, then you should always say it the first time, but after that, it's acceptable to just say it like this. You get what I mean? So, you know, microbes, bacteria have correct names, and this, it's called a binomial nomenclature naming system, where they have the genus and the species name. So, and it's acceptable after you've said it the first time to just say E, period, coli, okay? When you write them, and this is, I want you all to know how to write microbes names. I do. Or any species names. The genus is always capitalized. Always capitalized. The species is always lowercase. Lowercase, capital, okay? Now, if you are typing it, you would need to either italicize the whole name, because it's a formal name, or you need to underline it, always. Even if it's like this, you italicize it or you underline it. Just so you know that you're talking about the formal name of an organism, right? So this is how you would correctly write that. Now I forgot what I was talking about. Because E. coli. E. coli is the predominant of one particular group in your colon. The predominant organism in everyone's colon is E. coli, male, female, young, old, whatever. E. coli is one of the predominant bacteria that's in our colon. It gives us, it actually provides for us vitamin K. It helps with vitamin B absorption. So we need it, don't we? We need it. Do we not? We do. And it's in our colon. That's part of our microbiome in our colon. But ladies, post-puberty, hormones start changing at puberty, right? Tissues start to change, actually. Activity starts to change after puberty. Do you know what is the most common cause of females post-puberty, after puberty, cause for urinary tract infections? Do you know what bacteria it is? What would you guess? What I've been talking about is what? It's E. coli. So you would want to know that. And post-puberty females, and our urinary tract infections really common in women post-puberty. They're really common. And almost, not all of them, but almost all of them are caused from E. coli. Where did the women who had these infections get that from?
People, it's not right.
Well, it's their own E. coli, but because it's in a different location, it's been introduced to a different location, the urethra or the bladder, it's now going to take the opportunity to cause disease. So is the E. coli an opportunistic pathogen? Yes. Now you might ask yourself, well, how does E. coli get from the colon to the urethral opening or the bladder? Well, E. coli, there are several ways. In post-puberty, things are actually kind of changing, but hygiene can be one. Like, that's why girls get taught to wipe front to back, right? And so the other way. Urinating after intercourse is a huge way to prevent urinary tract infection, because when you urinate, are you flushing the opening of the urethra? So you're flushing that out. And so just the act that you urinate frequently, you urinate completely, this can protect you from having urinary tract infection. It really can. Not taking bubble baths or too hot of baths, because the tissues in this perineum region for females is very delicate. And even microscopic drying out or irritation can allow for this bacteria that's in everybody's male and female, young and old, perianal area. It can prevent them from setting up house. You know what I mean? So not using harsh soaps, not doing this. So not wearing too tight of clothing can set you up for this. So great. Now, but we're learning. Is E. coli a bad guy, or is it a what? It's a good guy. This needs to be in the right place, right? Right? Or it can take the opportunity to cause disease. Now, here's what I need you to know too. Most of the antibiotics that we use against true bacterial infections that need them, most of them are coming from other microorganisms. A lot of them are fungi, or microbes that we can find in the soil. So we use microorganisms that are in our environment because sometimes they're producing products that can fight against other infections. Penicillin. Where does penicillin come from? Let me give you an example down here. Where does penicillin come from? What'd you say? Mold. It's a mold, and the genus of the mold is called Penicillium. So it's a mold. It's absolutely right. And does it sometimes grow in our bread and our cheeses and our whatever? Penicillin is a mold. The spores are in the atmosphere. It grows places. It's fine. But it's a mold. Penicillium is a mold that produces a byproduct called penicillin that we can use to treat against bacteria. We'll talk more about that, but isn't that awesome, right? And so many of our antibiotics. Now, insulin is actually a protein that we produce. It's a hormone that we produce, right? We produce human insulin. Our pancreas produces human insulin. In our DNA, we have this if we open up our DNA and splice it at one particular spot, there's a recipe for insulin. Guess what we have done through genetic engineering? We have taken that human recipe out of that DNA and inserted it into our friends, our bacteria, that work for nothing hardly. They don't need breaks, they don't need cigarette breaks, bathroom breaks, they don't even sleep. All we have to do is be feeding them with the bacteria. We can insert that gene into their DNA bacteria and they'll produce insulin for us 24/7. And it's human insulin. I want you all to think about, before we had the technology that we could take a recipe out of a cookbook, human recipe, and put it into another species and get that species to make it for us. Diabetics were having to get insulin from human donation. And what were they dying from when they were having to get human donations? Usually infectious diseases they'd gotten from the human that we couldn't detect. But they were going to die from the diabetes. Does everybody get that diabetes, insulin-dependent diabetes, if you don't get insulin, your days are numbered? Everybody knows that it used to, a long time ago, be called a wasting disease because, as most of you know, insulin-dependent diabetes usually happens in childhood, doesn't it? And there's this honeymoon phase of it where they're still producing, for a while, they're still producing a little bit of insulin. But after a while, they're not producing any insulin, and then they die. And it didn't take very long. Before they died, they usually get wasted away to nothing, right? So that's what it was called. But then when we realized that what insulin was, there was a way that people were getting it through human donation. But you know who you're at the most risk for catching something from? Is it your dog? Is it the most dangerous risk? Is it your dog? Is it your cat? Is it your rat? And you can't get disease from them, but humans are the ones that you're most at risk for. So many of those diabetics before, it was also expensive, it was unavailable, and it was a risk. But then through technology, modern technology, now we can actually get microbes to make human insulin. And we can get them to do it cheaply and effectively, and we can make it pure, and there's no risk to it, and it's wonderful, right? So that's a great thing. And do you think insulin's the only thing? No, a lot of clotting factors. So people who had hemophilia, y'all remember what hemophilia is? If you didn't, write it down. Hemophilia is an inherited disorder where you are lacking one or more of the blood clotting factors that you should be able to make to clot your blood. So people who are born with hemophilia, most of them are lacking what's called factor VIII. And they die young because they would bleed to death from having a nosebleed, or they would bleed to death from falling down and scraping their knee. They would never stop bleeding, and they would bleed to death. So hemophilia, before modern technology, was really usually a death sentence unless you were in the royalty and you could have like little bodyguards. Most of us weren't born into royalty. The definition of hemophilia is a disease that is characterized, if you will, or caused from a lack of information to make blood clotting factors. Now, where do we get information for all of our recipes? We get them from our parents. So that's a genetic disorder, right? Did I say that? Are you good? Okay, all right, so, right. It's a genetic disorder. But now guess what we have? Just like we have bacteria making insulin for diabetics, we have bacteria and yeast too, that's yeast too. Bacteria and yeast that can make blood clotting factors. Again, cheaply, effectively, with no risk of catching infectious diseases because you got a human donation, right? That's a beautiful thing. Are we thanking our microbes for all this so far? Now, I don't know if you guys remember or read about, well, everybody knows about the EPA, don't you? What's the EPA stand for? What does EPA stand for?
Environmental Protection Agency.
Environmental Protection Agency, EPA. Do we know how long it's been around? since the late 60s, early 70s, actually it probably was 70 because in 69 was the Valdez oil spill. But the Environmental Protection Agency, what a lot of people don't realize is that our country, and really our country, is a lot better off right now today than it was in 1970. We tend to hear really bad news about things. We always hear the bad news. No, bad news is all. But what we don't realize is that our waters are cleaner. We have actually our forests are probably better, and whatever since the 70s because of the EPA, Environmental Protection Agency. And you know, I don't want to get into anything political, but I'm going to let you all know it's at risk right now. This administration's cut it by half. So I just need you all to understand that the EPA is very much at risk right now. And this administration, hopefully these things will turn around real quickly, but crazy at risk, some things that are happening right now. And if you really looked into just that one division, it would scare the hell out of you. I know people who work there, and I know things that are going on with the EPA. But anyway, so let me say this to you: when the Valdez crash, you know, that ship was carrying this oil, it was horrendous what it did. The oil spill that happened, and have we had quite a few oil spills since then? Yes, because we have these big tankers and you have whatever. So we've had a lot of oil spills since then, and ecosystems are being incredibly disrupted because of some of these pollution things that are happening because of human activity. But guess what we found out? We found out that there's some microbes that really love to eat oil. And when you put them out there, they're not even harmful to humans, but you put them out there and they will just gobble up all the pollutants that humans just put in their tank. And the byproducts they give off are just going to be gases and water sometimes. Like the byproducts are going to be friendly to us. So it's amazing. We can use microorganisms and effectively use, and we have been doing this. The EPA is a real leader in this. We've been using microorganisms to help us bioremediate, which means cleaning up the environment. Cleaning up the environment. So isn't that a beautiful thing, use of microorganisms, right? It really is. So how many of you like sourdough bread? Okay. Me too, Eric. So anyway, especially my sisters, especially if she's made instead of me. So anyway, but right, so we have food, we have wine, we have beer, we have all kinds of products, food products, cheeses, you know, things that we can't make without these microorganisms. It's required to have them to make these products. So look, even though really probably after today we won't talk much about our friendly microbes unless it's just in passing, please keep in mind it's just those few bad guys that are getting this whole attention, right? And it is just a few of them that actually get the attention. Do I have any questions about that? Y'all are good? Okay. I want to challenge you guys to this, and I hope that it's such a nice group. I think we're going to be able to do this pretty well. About midway through, I'm going to do something for you, but I want to challenge you to do it going forward. About midway through, I'm going to give you a list. It's actually a chart of the bacteria that are significant that cause disease, the viruses that cause disease, the protozoa that cause disease. And I'm not going to just give you a list of their names. I'm going to have in a column the disease that comes. And, you know, the fungi. So I'm going to give that to you about halfway through. I will give it to you now, but I think you all dropped if you saw the list. No, that's not true. But it's kind of significant. But the other day, how many did we put out? How many did we talk about? Staph aureus, Streptococcus pyogenes. We talked about E. coli. We talked, methicillin-resistant Staph aureus, as well as the other Staph, you know, nice Staph aureus. We talked about, I think I even mentioned Ebola virus, didn't I? So we've already talked. We talked about. I was thinking about the other day. C. difficile, Clostridium difficile. So see, the other day we talked about 4 or 5, and what I do is usually talk about a couple each lecture period, so that by the time you really got to like chapter or whatever it is, you wouldn't see that whole list and think, oh my goodness, right? So I want you to realize we start talking about these guys enough that they become kind of common names to you and friends that you'll think of. Because right now, if I were to ask you the next time we meet, what is the most common cause of urinary tract infections in post-pubescent women, you'd say what?
E. coli.
And you know it. You own that forever, right? So, so we're going to be talking about it all along. But about midway through, I will give you that chart. But what I'd like you to do now is maybe start keeping your own. After every lecture, if I've added a new microbe, I want you to have one page that's maybe just bacteria. And then you have a chart that you are looking at, that if it's a protozoa, that you put it under protozoa. Why do I care that you know when you hear a name that you know which category it belongs to? Why? Say that loud. That's it. That is the golden thing. So that when you hear a microorganism, you think, oh, that's a bacteria. What's going to work? Antibiotics, which we might have to have a particular antibiotic, but antibiotics. Or that's a virus. So I need an that's a protozoa. So we better be treating with a anti-protozoal, right? That's a fungal, that's a yeast or mold, so I better be treating it with an antifungal, right? So that's exactly what I want. And so if you all are kind of keeping your own little chart as you go, and you can sort of reviewing it as I add those names, by the time I give you that chart midway through, which by the way, is your final exam in this class, that chart I give you, and it's not going to be anyone we hadn't talked about, but that chart I give you is your final exam in this class. Every question would come from that chart. That's all you have to study. Put everything else away, and that's your final thing. Fair? So you kind of know. This class is about becoming familiar with microorganisms' names, knowing what group they belong to, and what disease they cause, so we know how to treat, right? So that's where we are, and that's what we're going to do in here. So when we think about this, these really are the different subdivisions or categories that we think of. Some of you may have not have heard the term helminth, but you can think of those as worms, okay? So these ones, because now you might be thinking to yourself, why would worms be like tapeworm, roundworms, and pinworms, and, whipworms? Why would they be in microbiology? Well, the reason that we include them here is because their diagnostic form is usually their eggs or larvae, and they are microscopic, right? It's nice when you get that diaper in, and I've seen several into the clinics, the pediatric clinics that had roundworms. And you go, okay, I know what this is. So, but a lot of times you don't get that. The only thing you get is a stool sample, and you have to be able to recognize the eggs, right? Okay, so this is one of the reasons. So know that that's kind of what this is, this category. Now, our planet and life kind of on this planet, when we think about life on this planet, I do, and I talked to you about, and I said to you that the foundation of life on this planet is actually microbial, isn't it? And it really is. And when we think about life on this planet, how old is the planet? Do we think? It's probably up there somewhere, right? So how old is the planet? Did you just say old? Old. I'm old too, but I'm not as old as the planet. Yeah, so I don't feel old. Old is just a frame of mind, right? All right, so look, so the planet is about 4.6 billion years old. 4.6 billion years old, or 4.6 billion years, I'll make this an A, so ago, billion years ago, right? The Earth. We know the Earth is approximately that old. Okay, so we get that. And we know if we think about this as being right now, right this second, well, that second's gone, but we're right here, right now, right? I want you to think about like life on this planet, because it's what we know now our planet is like, what we know the atmosphere is like, what we know our seas and our different biomes are like here on this planet. Is it like it was then? No. No, so the environment has really changed in 4.6 billion years. So it has really changed. We could sometimes refer to this, and we kind of know what it was like. There's testing that they can do to kind of know. They've done all kinds of exhaustive testing to kind of know what the primordial, they call it primordial atmosphere, and primordial seas were like. And I'm going to tell you, it was harsh compared to today. If all the life species that are present today, all the ones, and let's just think about insects for a second. There are more than 1 million different species of insects. Spiders, when you hear the fact that there's always in your entire life, from the time that you're born, you come home, to, until you die, there's a spider looking at you. That's a nice thought. There are a lot of spiders out there, even right now. So anyway, I don't know. But like right here in this area, there's like thousands of spider species just right here in this little area, but not in our room, but in our system here. But anyway, there's thousands of life species, millions of species of life present, and that's not including the bacteria. But if we took all the life species that are present right now in the environment that's right now, and we transported them back to here, would they survive? No, except for some that are in this group called archaea. Now, when you all see this word, and I want you to write it down. When you see this word archaea, what does archaea mean? Archaic means what? No, I see, that's arachnid. That's arachnid. But archaic means what? Oh, did you say? Oh, it does. So this is a group of microorganisms that are ancient. A lot of times you don't see it as archaea, you see it as archaeobacteria, one word. Archaeobacteria, one word. These bacteria are present today, they're present right now. Guess where they live? They live where we didn't even think life could exist, in the volcanic vents that are incredibly hot, right? They live in the Dead Sea that we thought was too salty for any life forms. They live in the permafrost that we thought was too cold for it. So these archaeobacteria are living today that are ancient life forms. So if we took all the life that we know, all the species of every single thing, and we transported it back, guess what is probably the only ones that would be surviving? Those archaea, the descendants of those archaea. Yes?
What was it actually you said the name of volcanic vents?
The Dead Sea, which is so salty. We thought that with salt, that life really did. I was just giving you some examples of really harsh environments that are present today in the permafrost, so ice. So there's been some, studies where we thought nothing could be, some places on the planet that we thought nothing could be there, but guess what we find? These archaeobacteria, they're there. Their life is there. Deep in the earth, where we have really high metal contents and whatnot. So we found them. But anyway, so we kind of get that. But there is life, and it's flourishing, and, all the species that are present today. When we look at species that have lived in between, we understand that 99%, and this is math, mathematicians do these numbers, 99% of the life that's just what we know about, that we found evidence of, is extinct, is gone. There is evidence that the life and all the flourishing life we see right now on our planet, we're only about 1% of what has been on our planet. The rest is extinct, has become extinct. Is that depressing? You think it's a little bit depressing? Okay, Karen, did you say yeah? This is a little scary. Well, so it's actually, there's some good news. Some good news is that life will persist on the planet in some form or another. Life will persist. What we know in this span is that there have been 5 major extinction events. We're right now in the 6th one. Now, do these extinction events happen all of a sudden, or do they usually geological time? It takes a while for them to happen. Sometimes there have been sudden ones, like we know that one of the last that took out the dinosaurs, as far as geological time, it was pretty sudden. And there are ideas that it was a meteor, it changed the atmosphere, changed all the stuff, food sources, whatever. Okay, so that was about 65 million years ago, right? Anyway, you don't even know that. But 5 major extinction events have happened where species have been really cut down in numbers. And then after that, the environment changed and the species that were remaining were able to continue to evolve, right? And then extinction, and the ones remaining had to evolve, and the extinction, and the ones that, you get what I mean? Now, you might actually say as human beings, and actually any species that's alive right now on the planet, we're happy that those happened. Because if those had not happened, is it likely that we would have happened? You get what I mean? Okay, so we're thinking about it. Now, what I'd like you to think about, though, and I've given this to other people, I know Derek's seen this in my other class. Again, mathematicians who got together, because we can't think of billions. Billions are too hard to get your head around actually what billions are. So we think about things we can correlate it with in a mathematical way that will be kind of equal. And so what people can usually visualize is how long a year is. Because you can think about what you were doing in January, and then maybe up to Easter, and midsummer, and then fall, Thanksgiving, Christmas. You can think about a year. So I want you to know that mathematicians have put this into a year. They have crunched it down into the birth of the planet into where we are right now, into a year. So this is like January 1, and we are right now 1 second from the new year, right? So what month do you think did life show up on the planet? What month do you think? Because we don't think, actually some evidence just showed up for earlier life that we just found some evidence of earlier than we even thought. That just got discovered this year. What'd you say? Well, very good guess, because it's around March. It's like March, they were saying mid-March, but now it's actually maybe earlier March, because we have found evidence of even a more ancient species. Because we know this was rough. It was rough in there. And then as the environment started to change and life existed, that we see single cell life. We're not talking about little warm and fuzzy creatures. We're talking about microscopic single-cell life form here. Okay, but now what about the complex life form from single cell? What about like algae? And because algae is life form, and algae and plant life. When did that show up? We're thinking around. Yeah, it was truly. Well, it's not, we're not talking, this is just giving you a perspective. So the earth is changing, isn't it? So it really was around June that we're thinking about some of the earlier plants. So when did dinosaurs show up? Because is the atmosphere changing? By the way, the atmosphere where the dinosaurs survived, we couldn't survive. The atmosphere, we couldn't really survive the way we are now. There was way more oxygen in the atmosphere then than now.
Late August.
So actually, the dinosaurs showed up at Thanksgiving Day. So that's late November, isn't it? That is like whatever Thursday that is in November. Is it the last Thursday in November? So you're talking about Thanksgiving Day, late November, the dinosaurs showed up. When did the dinosaurs disappear from the planet? They disappeared around December 16th. Or so, the evening of. Wow. How long have humans been on this planet? Close to. But actually it was late, like I think it was what the mathematicians say, like December the 26th or something, late in the day too. So like the 26th humans showed up. And hey, by the way, the humans that showed up, the early humans, was it Homo sapiens that showed up, or was it like, I call it, one of the earlier ones is Lucy. Her name was Lucy, for Lucy in the Sky with Diamonds. Anyway, but that's how they named her. Did anybody know that? Okay, y'all actually. Is it? Yeah. Okay. So Lucy, who was all of ours, grandma. Every one of us. Come here. I mean, really, we think about it. We think about it. We are so related. We're so closely, intimately related. All humans on this planet. All of us. We're all related. Lucy would have been a runway model in her day. I know she doesn't look like what you think of as humans, but in her day, she would have been, right? And from Lucy, now we're just a few days later, and we're where we are now. So this gives you kind of an idea about life on the planet and where life came from. But what we understand is that microbial life, we are dependent on microbial life on this planet. I think you kind of gotten a sense of all the good things that this microbial life does. And we better learn and know as much about it as we possibly can, because what might happen if we don't get a handle on this information? Look, if 99% of the species that have ever been on this planet are now extinct, it is likely that what species will become extinct? Exactly. And this sixth major extinction event right now, it is no question about what is putting us in that. It is human activity. Human activity is put us into the sixth major extinction event. We are encroaching on so many habitats of so many species, and what we might not be realizing is that we are going to take out a keystone species. All life on this planet is interwoven, and if we take out a species or two that we're dependent on, there may be no going back. Do you get what I'm saying? Do you hear what I'm saying? So the more we can know, the better about our species, right? The better chance that we might have a chance to have a longer reign than the dinosaurs did. Because I'm going to tell you something. Most scientists don't think we'll have nearly as long of a range as the dinosaurs had. Because this was a long reign here that they had. Reign. They had a really long reign. Right? Anyway, okay, that's really something depressing. It's not depressing. It's, knowledge is actually a good thing. It's not supposed to scare people. It's a good thing. But this is just looking at some of how we know some of this has actually occurred. And let's see what else I want you to know. The coolest thing about microorganisms, we know we're dependent on them, but things that we can really use them for. We can use them to see how other life forms actually function. So one of the things that's great about them is that they reproduce quickly. They're single-celled organisms. They're dictated by the DNA, aren't they? Just like who is? We are, right? So just like we are, I said that weird, but anyway. So they reproduce rapidly. The average reproduction time, that some of them have longer, some of them have shorter, but the average reproduction time for a bacterium, let's say, a common bacterium, is going to be about 15 to 20 minutes. So you can have one, give it a little food and a broth and a temperature that it likes, and in 20 minutes, guess how many you got? Well, you only start with one, so then you have two. But in another 20 minutes, you have 4, and another 20 minutes, 8. You get what that means? In 20 divisions, 20 minutes, if you will, you got 1 million. And were they the same as the first one you started with? Yes, they are identical. So bacteria it's a type of cloning that they do when they divide. And they really don't need a lot, right? They need to be in the right atmosphere, the right temperature, and a little bit of food. And it's kind of nice. And so anyway, and we will look at them through microscopes, so we'll definitely take a look at some of these, but they're great to study because they really function on a tiny, tiny scale, very much like our cells have to function. So they're a great things to study. So life has been on this planet, single cell organisms. Now really, they're thinking about 3.8 billion years. So I would give you close if you said, but put down 3.8 billion years ago. Life is, we know life at this point, we think life actually started on the planet. Was it complex life? No, it was single cell microbial life. Exactly. Now, I want you to know these three categories that microbiologists call domains. Microbiologists call these domains, and we study life on the planet from these three domains. The three domains are going to be bacteria, and if you will, you put by bacteria. Certainly, they're single cell; they don't have a nucleus. But put by that in parentheses one word: EU bacteria, because you'll see that group referred to as eubacteria, EU bacteria, which is pronounced eubacteria. What does EU as a prefix mean? True. It means true bacteria. That's exactly right. And then there's a domain called archaea, and y'all told me that those single-celled organisms, they're what? Those guys can survive almost anything, right? These are ancient life forms, right? In bacteria, and sometimes you see that as archaeobacteria, one word, but y'all will know that means the same thing. And then the third domain that microbiologists use for life is something called eukaryotes. Eukaryotes. Again, you meant true. Carry-on is nucleus. That's Latin for nucleus. So these guys have a what? A true nucleus, meaning that they're complex life forms. These are complex life forms. They have organelles. The cells have organelles. Where bacteria, are these guys complex? These are simple celled organisms. They're not very complex. And they're not, okay? But eukaryotes are. Now let me remind you all of something that you probably all remember. Y'all probably remember in biology in high school or elementary school, you remember learning about kingdoms, don't you? Do you remember kingdoms? What were the kingdoms of life that you learned about? What were they? What were the kingdoms of life that you learned about? What? You learned about animal kingdom, didn't you? The plant kingdom, fungi, and protozoa, didn't you? Proteus, protozoa. Do y'all remember that? Does everybody remember that? All right, well, let me say this. There are 6, when you think about these 3 domains, sometimes they're broken down into 6 kingdoms. So let's look at the 6 kingdoms. Make sure we know the 6 kingdoms. One of the kingdoms is archaea. One of the kingdoms is eubacteria. And then under the eukaryotes, there are 4 kingdoms. You ready? So under that eukaryotic domain, there are 4 kingdoms. Those kingdoms are protists, fungi, plants, and animals. And they're under these eukaryotes. They're complex. Plants are complex. Fungi are complex. Protists. Yeah, right? Are we good with that? So this is just a classification I'm kind of giving you. You hear it? You seeing that? I'm sort of giving you this classification. Let me tell you about these 2 domains, which also happen to be their own kingdoms, right? Your bacteria and archaea. These 2 domains are said to be prokaryotic. What does that mean? When you hear that word, you'll just know, what does it mean? It's against. Pro is in this case means before a karyon, before a nucleus. These don't have nuclei. So they're very simple. They don't even have organelles, and they're little tiny cells. Pro, it's this with a pro in front of it instead of you. And that's what these are. So if you hear the term prokaryotes, you know you're talking about bacteria, aren't you? It might be archaea, or it might be just true bacteria, but you're talking about bacteria and your prokaryotes. Fair enough? Eukaryotes had 4 kingdoms. What are they? Protists. Protozoa. You've heard of protozoa, so protists. All right. So we're kind of getting organized. We're kind of classifying things. We're kind of thinking. Okay, so that's what we're doing. And when we think about these are single cell. We think of them as single cell, these bacteria. But when we look at the eukaryotes, almost, not all of them, but, well, that's weird the way that it's written. But in eukaryotes, we really think about them as being multi-cell. We really do, because fungi, plants, and animals are multi-cell. Now, proteins are single cell. Proteins are single cell. And they're large cells. These are huge cells, huge cells. Eukaryotes have huge cells. They have organelles inside of them. What's an organelle? Write that word down. What's an organelle? What's an organelle? Give me an example of an organelle. If this were a cell and I had an organelle here that held the DNA, what is that organelle that's housing the DNA? Does anybody remember what that organelle is called? It's a nucleus. So an example of an organelle is a nucleus. And then some cells have this, what are called powerhouse organelles. What are they? Mitochondria. Remember that? So mitochondria, nucleus. Okay, so those are two examples of organelles that, what kind of cells have these potentially? Eukaryotes, right? They're complex, they're big cells. They're carrying out various complex kind of life forms that we'll talk about. Again, what are 4 kingdoms in the eukaryotes? Because you will have to know that.
Proteins, fungi, plants,
And this is misleading to say many are single cell, but some are single cell. But most of those kingdoms are multi-cell, really. Most of those kingdoms really are multi-cell. So, okay, great. Now, here's what I want you to know. We have a few minutes to talk about this theory of evolution and theories in science. Guys, theories in science. A scientific theory is, and I know some of you have sit with me talking about this before, but it's just so important because there's so much misinformation, I think, in many of the school systems about scientific theories, and especially maybe theory of evolution and whatnot. All right, so here's what I want to let you know. When you use the word theory, and I, myself included, when we use the word theory outside of science discussion, we often use that word thinking about this as an idea, don't we? And so I have a theory about why he acted that way. Or I have a theory about why that student did something. Or I have a theory about, you know, the Bachelor and carried all this thing, what's going on in the show. And we might become extinct. Okay? Oh, no. Right. But anyway. So, anyway, I just want to let you know. So it's used differently because that, in that sense that you're using theory, it's like, okay, well, I have an idea and I can express that idea. That's my theory, I'm sticking to it. Right? That's my story and I'm sticking to it. That's not how theory is used in the science. A scientific theory is, it certainly is an explanatory statement about a naturally occurring phenomenon. Scientific theory is an explanatory statement, means it explains how this natural event is happening. It's a statement that tells you something. A scientific theory is only accepted by the experts after exhaustive study using the scientific method, using facts, using laws, and again, exhaustive kinds of research. A statement will be made that explains a naturally occurring phenomenon, and that's a scientific theory. Are you with me on that? Now, the truth is that if more data starts to come in, and new research, and new studies, and new proof, that explanatory statement needs to be discarded or tweaked or whatever, then it has to be changed in true science. But the scientific theories that we have today, the cell theory, name some, the cell theory, the theory of evolution, the germ theory of disease, right? These are ones that we'll be interested in. The germ theory of disease, There's all kinds of scientific theories that are accepted today. They're the best thing we've got by the best minds that we've got, explaining naturally occurring phenomena. The limits of science, though, are that science is only about the natural world, not about beliefs. If a scientist is trying to tell you something about a belief thing, that's not science. We have to realize we're limited. The scientific community is limited to the natural world, naturally occurring events and phenomena. Not about beliefs, not about, other things. No. Just about what we can prove. Can we prove everything in science? No, there's some things that can't be tested. Beliefs can't be tested. They can't. So we have to leave those at the door and realize we can't test those. We're not even trying to, or judging them or any other way. We're just looking at a natural event that's happening in the world and asking why. Does that happen that way? Or how does that happen? And you get what I'm saying? So it's limited. Science is limited to the natural world, and scientific theories are exalted explanations. They really are. So in an informed society where students are learning, it's criminal to not give the best information that the best minds have today. You get what I mean? We still have schools in this country that won't teach scientific theory. They won't teach it because it goes against their beliefs. But is it supposed to be separate? That's separate. Scientific theories are not supposed to be encroaching on beliefs, and vice versa, right? So whatever you think, I don't care. But I'm just letting you know what the best science today says, that the theory of evolution is this. And I'm gonna give it to you, and we've got to go. Here's the theory of evolution. And if you look at this time scale, this feeds into this, okay? Because we said we're right now, and right now the species, the 1%, really less than 1% of all the life that's ever been on this planet right now, that's alive today, existing on this planet today, actually came from descendants, right? We do get that. But we know that we don't look like Lucy did. And we don't, even though she was our grandmama, all of our grandmamas, or somebody like her, closer, like, right? So we get that. We get that we come from that. But we have to think about, why do we look different? The theory of evolution has nothing to do with an individual evolving. That's in your psychology, your sociology classes. Yes, we can evolve. Yes, we can grow. Yes, we can do. But that's not the theory of evolution. The theory of evolution is about species and change within a species over time. And the only thing that it is about is the change in the percentage of traits that you find within that species over time. Did I tell you all that Lucy, I know y'all seen pictures of Lucy if you saw the documentary, and you might think, I didn't come. Yes, we did. Yes, we did. But the species, she wasn't any different looking than her sister and her brother. She wasn't very different looking as far as the traits went. The percentage of traits found within that species at that time has changed to now, hasn't it? Or we would still be looking little and hairy. And do you get what I'm saying? So the theory of evolution simply states that the percentage of traits found within the species will change over time due to environmental pressures. That's all it states. That's all it states. It doesn't state anything about beliefs. You can still have your beliefs, right? But it states that, and there's exhaustive evidence that that is really true. It actually is happening even in your microbiome. It happens in your microbiome when you take antibiotics. If you change the environment, you change the species, the traits in the species. That makes sense? All right, how are we feeling? Are we feeling all right? Yeah? Everybody's good? Is everybody on the roll? Do you think y'all can all see the canvas pile? All right, so, all right.
so do you have any questions for me, anybody?